we're moving from blockchain fundamentals into Besu architecture. A Besu node is the execution engine that processes transactions, runs smart contracts, stores ledger state, and connects to public or enterprise networks. This foundation will frame everything that follows. Up to this point, we've positioned Besu as an Ethereum-compatible client, compared public, private, and permission models, and considered when it fits enterprise use cases. Now we shift inward to what a Besu node actually does as it processes transactions, stores state, validates blocks, serves APIs, and communicates with peers. A Besu node is the active software process that lets a machine participate in an Ethereum-compatible network. It stores blockchain data, talks to peers, checks blocks, and runs transactions through the EVM. It also provides APIs, so applications and operators can read data, submit transactions, and manage the node. Think of Besu as the execution layer that determines what transactions actually do. Applications and wallets send requests through APIs. Besu runs the EVM, applies smart contract logic, updates account and contract state, and checks that blocks follow execution rules. It also syncs with peers, so its local view stays consistent. On public Ethereum, consensus is handled alongside a separate consensus client. In private networks, Besu can participate in consensus depending on configuration. A Besu node is not doing just one job. It coordinates several responsibilities at once. It receives pending transactions, shares them with peers, and prepares them for inclusion in blocks. It executes those transactions through the EVM, then records the resulting state, receipts, logs, and block data. At the same time, it exposes APIs, maintains peer connections, and validates incoming blocks, so its local view remains synchronized and trustworthy. A transaction usually enters Besu through JSON-RPC, often with ETH and raw transaction. Before it can affect the chain, the node checks that it is well-formed, correctly signed, uses the right nonce, can pay gas, and has sufficient balance. If it passes, it waits in the transaction pool and may be shared with peers. Once included in a block, it is executed by the EVM, updates world state, and produces the receipt and logs applications use for confirmation. The EVM is Besu's deterministic processor for smart contracts. It takes a transaction, the prior state, and block context, then runs bytecode according to Ethereum rules. Gas metering provides the safety boundary, charging each operation and stopping execution if limits are reached. The result may update balances, contract storage, and logs. Because synchronized nodes follow the same rules, the same inputs produce the same transaction outcome. World state is Ethereum's live ledger snapshot, the latest result of every transaction executed so far. That snapshot is made of account states. Each account tracks a nonce, balance, storage route, and code hash. Externally owned accounts are controlled by private keys and initiate transactions with signatures. Contract accounts are controlled by code. When transactions execute that code, contract storage changes, and the world state changes with it. Besu's database is more than a chain of block files. Each block includes a header, transactions, and a link to its parent. After execution, Besu stores receipts that record status, gas used, and outputs. Smart contracts can also emit logs, which dApps often watch as events. Separately, Besu maintains state data, including account balances and contract storage. Indexes connect these pieces, making historical lookups and operational queries fast enough to be useful. When a contract runs, it can update its own persistent storage, such as balances or ownership records. It can also emit events like a transfer event, which become searchable logs. After execution, the transaction receipt records the outcome: success or failure, gas used, any new contract address, and the logs produced. Off-chain applications watch these receipts and events so databases, dashboards, notifications, and user interfaces stay aligned with blockchain activity. Storage sits in the critical path for synchronization, transaction execution, validation, and API queries. That means storage choices directly affect node health. Fast SSDs and sufficient IOPS reduce latency during frequent state reads and writes. Archive-style workloads require much larger capacity than normal full nodes. In enterprise environments, treat storage as an operational service. Monitor growth, back it up, define retention, and test recovery. Besu's JSON-RPC endpoint is the main doorway for applications. Wallets, backends, monitoring tools, and scripts use namespaces like eth, net, web3, admin, and txpool to read chain data, estimate gas, inspect blocks, and submit transactions. Because that doorway is powerful, production access should use controls such as TLS, firewalls, allow lists, and authentication proxies. Expose only what each client needs, and never make administrative APIs public. That protects the node without blocking legitimate traffic. Networking in Besu is peer-to-peer, so each node both requests and shares information. Peers exchange new blocks, pending transactions, and status messages that help them stay synchronized. On public networks, discovery lets a new node find peers dynamically. In private networks, you usually control that process with boot nodes, static peers, or allow lists. The goal is steady connectivity. Reliable peers support faster sync, quicker block propagation, and better resilience when some nodes fail. When a Besu node receives a block, it treats it as a claim, not a fact. It checks the header, parent link, gas limits, and every transaction. Then it re-executes the transactions locally and compares the calculated state route and receipts route with the block's declared results. If anything breaks protocol rules, the block is rejected. In private networks, that validation works alongside consensus and permissioning, so only authorized, valid history is accepted. You now have the foundation. A Besu node executes EVM transactions, updates state, stores blockchain data, exposes APIs, connects with peers, and validates blocks. Together, these pieces shape reliability, performance, and operations. Next, we move from understanding a single node to designing networks, starting with consensus mechanisms in Besu.